you have to ask questions. Over to Matthew.
Thank you. It's a pleasure to give this talk, and thank you for the invitation. This talk is kind of hard to give, so I do not know if it's hard to give or hard to listen to, or both. So please interrupt me. Don't start raising your hand because I will not notice it. And this is a relatively small group of people. So please just jump in and ask for clarifications. I try to be as clear as I can. So over the last year or so, I was interested in the topic of fractons because they pose a very interesting challenge to quantum field theory, and I will soon say more about it. And this was the first paper I wrote on the subject, so this was in September, but in March, over a period of 30 days, together with Shuhan Shah, we put out 3 long papers and presenting our view of the topic of fractons. We only scratched the surface of the topic of fractons. Since this is a huge body of work, we published over 170 pages on the subject. There are various ways of giving such a talk, and one of them was to focus on one example and analyze it in relative detail, and that's what I will do here. So I'll talk mostly about work in this paper, which is a series of models in 2+1 dimensions. The most interesting models, so these 2 papers are mostly about physics in 3+1 dimensions, and this paper is the most interesting because it presents the most sophisticated model we analyzed today, and it's much more interesting than all the others. So one option would be to give an overview, scanning many models, and you will see the richness of the subject, but you will not be able to get into the detail. The other is to discuss the most exciting model, which is really fantastically interesting, but then it will not clear what the various ingredients are. And what I decided to do here is to describe the first set of models in this paper. And if you're interested in reading the paper, you're more than welcome, of course. But there were also 2 talks that Shuhan and I gave, but longer than this one, 90 minutes, my talk, which was an expanded version of this one. And then Shuhan gave another 90 minutes focusing on this paper, and to some extent this one. And they are available online. It was at Harvard Center of Mathematical Sciences. So the talks are available. So if you're really interested, you can go there. It might be that after you hear this talk, most of you will say, okay, we've heard more than enough. There's no reason to go to the other talks. So let me start with the introduction. It's very common in physics that we started short distances with some microscopic models, for example, some lattice model with some spins or whatever you want, some local interactions between them. And the lure is that at low energies, this lattice is not important. Physics becomes a continuum. Instead of a lattice, we have a continuum, and we describe everything using the language of continuum quantum field theory. And this lore has been working extremely powerful. It basically dominated a number of branches of physics, including condensed matter physics, high energy physics, etc., for decades now. So this is not something that we should abandon lightly. It also has an application, which is one of the main reasons this is interesting, is that the continuum low energy field theory, the continuum field theory, captures the universal aspects of the short distance physics. And it's not sensitive to most of the details of the short distance physics. In that sense, it's much more effective. In fact, that's why it's called effective field theory, because it captures all the interesting information, but not the irrelevant information. Having said that, in the last few years, and it's really a small number of years, some models came out from the condensed matter and actually also from the quantum information community, which present notable counterexamples to this lore. And these are very concrete lattice models. So there's some spins and local interaction, which looks totally innocent, but the long distance behavior of these systems cannot be captured by continuum quantum field theory. And I will review them on the next slide, and it will become clear that they're quite bizarre and they really do not fit this framework. And this is challenging for many different reasons, because what it really tells us that we should really expand or extend the framework of continuum quantum field theory in order to accommodate such models. And the extension should not be too drastic because we don't want to throw away all the successes of continuum quantum field theory. Also, continuum quantum field theory is a very tight topic. You cannot easily mess with it without ruining the whole thing. So we should try and extend it as little as possible, but something will have to give, and we will need an extension of the standard ideas. So there are two motivations for doing that. One is related to this point. We have all these lattice models. We would like to organize them in an effective way. And one way to organize field theories, behavioral phases of systems, and so forth, is to write down a continuum Lagrangian. So we would like to have such universal description of these systems that will tell us how to organize them. The second aspect, which I think is not less important, is that this will teach us something new about quantum field theory. Because if we are going to start messing with the things that we always take for granted, all the things that we cherish about continuum quantum field theory, as I said, something will have to change. Then hopefully this will teach us something about quantum field theory. So let me first tell you why these systems are so bizarre. There are many models and they exhibit different properties, and there isn't a clear classification of them. It's not clear what's going on there. People just stumbled on examples and then they call them type 1, type 2, but there's a problem mostly through how they stumbled on them. And they're characterized by a number of peculiar things. Not all models have all the peculiarities, but that's kind of very rough. First of all, they're particles of restricted mobility. So there are excitations of the system, particles, and the particles can be stuck at a point and cannot move at all. It's not that it costs a lot of energy to move them. They cannot move at all, period. There are also particles that are restricted to live on a line. So they're free to move, say, along the x direction, but they're not allowed to move away from the x direction or a plane here. So that's the first peculiar thing. The second peculiar thing is that there's an infinite ground state degeneracy in the continuum limit. So parenthetically, let me define the continuum limit. We have a lattice spacing A, we take it to 0, holding this the system at fixed sides. So Li, big Li, is the number of sides in the I direction on the lattice. This is the physical length, little Li, and we take the limit A going to infinity with fixed sides. We could also take other limits, and people study various limits, fixed lattice spacing, and the number of sides going to infinity. This is kind of more of a thermodynamic limit. We will be interested in the continuum limit, and I define clearly what it is. And many of the things I will say are not true if we take other limits, but that's the limit we will study. So if the number of sides goes to infinity, with or without A going to 0, the logarithm of the number of states in the simple model scales linearly in the number of sides in the x and the y and the z direction. And in some cases, it's much more complicated. It's not even monotonic. And there are various peculiar things about it. First of all, the ground state degeneracy is infinite. Second, the ground state degeneracy depends on the size of the system. It depends on the number of lattice points, not just the physical size, but it actually depends on the number of sites in the lattice. So it's very UV sensitive. These systems also have various exotic global symmetries. In the quantum information community, these are called logical operators, but for us, these will be global symmetries. And the symmetries will be unlike ordinary global symmetries that we are all familiar with, and they depend on position. The global symmetry depends on position, and as we change the position from point to point, the value of the charge jumps around. It's not a continuous function. So all these properties, the exotic global symmetries, charges jumping around, the ground state degeneracy, and so forth, tell us that as we go to low energies or to long distances, there is some dependence of short distance physics. And this is something that I've been interested in for decades. Many people have been interested in it for decades. I even wrote a paper with Shiraz and others on the topic. We called it UVIR mixing. You are at very low energies and you are sensitive to high momentum modes. And I'll say a lot more about it later. So all these features seem impossible in standard continuum field theory.
I have a question.
Yes.
Yeah, so you had just said that the global symmetry varies from point to point. Why is it not then a gauge symmetry?
Because it does not depend on time.
I see.
So gauge symmetry means that it depends at different times we can have a different charge, and then the Hilbert space has to be invariant under the symmetry.
Okay.
Or has to transform like as a phase under the symmetry. But here is a global symmetry. These are operators that commute with the Hamiltonian. They cannot depend on time. And there are operators in the system that are charged under the global symmetry. In a gauge symmetry, there are no operators charged under the gauge symmetry. They're not gauge invariant, and therefore you shouldn't study them. So anyway, all these things are impossible in continuum quantum field theory. So something
I also have a question, if you don't mind. So are you considering a relativistic theory here, or it's not?
I will. It's not going to be relativistic, and that's exactly what I'm going to say in the next slide.
I see. And the lattice is a finite size. Does it have a boundary?
So I'm considering lattice with periodic boundary conditions. We can also consider a boundary. So there are many things that we can change. I'm going to limit myself to the simplest state. So periodic boundary conditions and so forth. Now, and you will see that there is enormously complicated structure already here. And I'm also going to make all sorts of other simplifying assumptions along the way. Now, we can start in making the models more complicated, and then it would be much more interesting.
Okay, thank you.
Nati, just one question regarding the previous slide. So you had mentioned these 3 points. Is there some way they're obviously related? They seem very unrelated at this point.
Okay. Yes, that's an excellent question. So the third one is not really a point. You're talking about these 3.
Yeah.
As it stands here, they seem unrelated. And for all I know, there are also 4 points. I do not know of a systematic way of stating all the facts. So these are just some properties of them. In certain contexts of some of these models, you can show that, and this is actually something I'll show later in the talk, that this fact and that fact are actually closely related. Okay. In other models, the exotic global symmetry and the restricted mobility are related. I will also discuss models in the talk today that have exotic global symmetries, but we do not have this fact and this fact. So in that sense, they're not obviously related. But I brought them here because they're kind of the generic characteristics, and every one of them seems peculiar, if not impossible, in the context of continuum field theory. But things will be a lot clearer when we get to a concrete model and we start analyzing it.
And just one more question. So when you say about this restricted mobility, these lines and planes, are they dynamical? Are they like D-branes? Can they?
No, they're completely rigid. So you have a system that has so it's a chunk of material. Well, we don't have a real material, but it's a continuous region. And there are some excitations that can move along the X direction, other along the Y, but they cannot wiggle around.
Okay. Thanks.
And I'll show examples later. The perspective I'll present here will be mostly a continuum field. I try to fit all that into continuum field theory language. And in the course of doing that, we've learned quite a lot about the way the condensed matter people think about it. But that's not what I will do here. Here I will mostly talk about the condensed matter way of thinking. I try to fit all the examples that they have into high energy / continuum field theory framework. So we need to have new elements, and just by looking at the examples, it's easy to see that they are essentially unavoidable. So one might need to expand the framework even further beyond what we did, but whatever place we relax some of the assumptions that are normally taken for granted, this assumption that we relax is essentially unavoidable just by looking at the examples. And the first thing has already been alluded to in one of the questions here, the space-time symmetry. So we're going to have translations in space and time. So the medium is continuous. We don't just have lattice translation, but we have continuous translation. We don't have Lorentz invariance, but a little bit more interesting, we also will not have full rotation symmetries. We'll preserve only a subgroup generated by 90-degree rotations. That's true in the answers, and it might or might not be surprising if you start from a lattice model that has some orientations for the orientation of the lattice. One might extend that and consider other subgroups of the rotation group, but that's what we did. The second ingredient, but this is not really surprising, these facts. The fact that the space symmetry is restricted is extremely common, both in continuum field theory and in condensed matter physics. We can just put a background that violates the rotation symmetry, and that's it. Magnetic field in the x direction, electric field in the y direction, and we don't have rotation symmetry. We will have exotic global symmetry, and then we'll have exotic gauge symmetries. That's a little bit less standard. I'll define these as global symmetries. I will not have a complete classification of them, but I will present examples. We'll start with U1, and then we'll study Zn. First, the global symmetry and the gauge symmetry. That by itself, I don't think it's surprising, and is not really extending what we do in quantum field theory, except for the next ingredient. So this ingredient, I think, is the one that is most dramatic and most significant. And again, I emphasize it is essentially unavoidable. In continuum quantum field theory, we use continuous fields. So space-time is continuous, and we have mapped from space-time to a target space, and the maps are continuous functions. Here we will allow discontinuous functions. And again, this is really quite different than what we are used to. Discontinuous functions that we will allow, and we'll characterize them in a lot of detail, which discontinuities we allow and which we do not allow. These fields will not be as discontinuous on the lattice. On the lattice, everything is discontinuous. On the lattice, everything is discontinuous, but our fields will not be as discontinuous on the lattice. They will be more smooth than on the lattice. But on the other hand, they will not be as continuous in the continuum. So it will be kind of in between. And the fact that they are not as discontinuous as on the lattice means that we throw away a lot of the lattice stuff. So what we have is more universal than on the lattice. But I do emphasize that we'll have some discontinuities that will remain. We'll also study gauge theories, and the gauge parameters of the gauge theories will also be as discontinuous as the fields we discussed here. So the gauge parameters will also allow some discontinuities. And if the gauge parameters have discontinuities in them, the transition functions in twisted bundles should also have the corresponding discontinuities. But despite all these discontinuities, the answer we will get will be universal, and that's mostly because it's not as discontinuous as it could have been on the lattice.
Sorry, Nati, may I ask a question? Sorry, you'll probably come to this, I'm sure, but the excitations you were referring to, will they have finite energy in the continuum limit? I'm worried.
Yeah, this is an interesting question. There are two perspectives on all of these systems, and that has nothing to do with this particular examples. When we discuss a low energy continuum quantum field theory, which captures only the low energy excitations, various lattice excitations that carry charges are viewed as proparticles. They are not dynamical excitations, but they are proparticles. The way the continuum field theory captures them is by defects. So a low energy continuum physicist will say, the system doesn't have that as a dynamical excitation, but we can ask for the response to such a particle by throwing in a defect, and the defect has some word line trajectory, and here is another one, and the low energy observer can compute the effect of the interactions between them. Somebody else would be more ambitious and say, no, I want to describe also all the excitations. That's possible. Most of the condensed matter literature is about describing such excitations, but most of it is not going to be universal. The main reason we would like a low energy continuum field theory is that it will capture the universal aspects of these excitations without getting into the details of these excitations. And I don't know if this particular example helps you. A popular model in condensed matter literature is the toric code, the Times toric code, and it describes electric and magnetic excitations, and they braid, etc., etc. At low energies, this is a continuum Z2 gauge theory without these dynamical excitations. So in the continuum limit, these excitations go to infinity, and my goal here is to really zoom on low energies and find the analog of the Z2 gauge theory. Just as the Z2 gauge theory is the continuum limit of the toric code, in fact, historically, the Z2 gauge theory existed long before the toric code, but the relations between them will be identical to the relations I'll present here, the models I'll present here, and the continuum models in the lattice examples that people study.
Okay.
So I should qualify some things. We do not have a general systematic presentation of all of these models. Our understanding is incomplete. I'll say more about the incompleteness below. And we were motivated by specific examples, so we decided to stick to these specific examples and try to fit them rather than have an overarching perspective. I wish I had an overarching perspective, but I don't think we have it yet. And we studied 11 different models in the 3 papers. Some of them turned out to be dual to each other. So we had altogether only 6 distinct models. And in this paper, I will discuss only a few of them. So now, 21 minutes after the beginning of the talk, I finished my introduction, and I can get to the talk itself. And the first model I'd like to discuss is actually a model that does not have a fractons at all. It's a 2+1 dimensional lattice model by these 3 people. And in every one of the models I'll discuss, I'll first present the lattice model, then the continuum model, then we'll discuss the continuum physics coming out of the continuum model. So on the sides of the lattice is 2+1 dimension, 1 is time. We have phases, so it's like in the XY model, and conjugate momenta. And the Hamiltonian has a standard unsuppressing dimensionless dimension for coefficients and so forth, otherwise the equations will be cluttered. We have a momentum square, and normally we have a cosine of phi of the link, phi phase from one link minus the phase at one side minus the phase at the near side, and the difference between them. Here instead we have linear combinations of phi's around plaquettes without the link terms. So this is a well-defined lattice model. Everything is finite, everything is meaningful. We can think of if the lattice is finite, then the coordinate space, the phi's, are just a bunch of circles. And this is an interacting model, but in principle, you can imagine solving it. So completely well-defined. And as I said, we exclude nearest neighbor couplings, and we exclude more generic next to nearest neighbor couplings. So this is the full model. And one question which immediately comes to mind from a high energy perspective is this model natural? Namely, we have left out some coupling constants. Is it natural to leave them out? And the answer is yes. The model has what is called in the condensed matter literature subsystem symmetry. We look at the lattice and we rotate all the phi's for fixed x, called x0. But for every value of y, we shift it by the same amount, and we don't touch the phi's for other values of x. This is a global symmetry of the system because the momentum clearly commutes with this operation, and each cosine has 2 of these guys with opposite signs. So this is a symmetry. So the symmetry acts separately at each value of x, and there's a similar one that acts separately at each value of y. So we can also phrase it as follows. This is a subsystem symmetry. We can say that we can shift the field phi by an arbitrary function of x plus an arbitrary function of y. So if we take the Hamiltonian or the Lagrangian and we shift phi as follows, is like this, then nothing changes. So if we have a lattice with Lx sites in the x direction and Ly sites in the y direction, we have Lx functions here, Ly functions here, and we subtract 1 because of the common 0 modes between them. So this is a huge global symmetry, and it's clearly not a gauge symmetry. We cannot, somebody asked before, because we cannot put time dependence here. So this is all I wanted to say about the lattice system. It's an interacting system. We cannot solve it analytically, but we can start studying it numerically, and people study these models and various cousins of it numerically. Let's try and write a continuum model for this. So we're taking the coefficient in front of the potential to be large. That's what we normally do when we look for a continuum model. The coefficient here is large, so all the plaquette phases have to be very small. And if they're small, we can expand and we have a double derivative of phi. And A is the lattice spacing. So if we take a continuum limit, this would be our Lagrangian. From the kinetic term, we get phi dot square, and then we get minus dx dy phi squared, and phi is a periodic variable. Now I emphasize that even though the original lattice model is interacting, this theory is Gaussian theory, because it's quadratic in phi. And since it's a quadratic function of phi, there is really no excuse not to get the answer straight. Right? This is a free field theory. As you will soon see, it's quite subtle, but it's still a free field theory. So there's really no room to hide. So in the coming slides, I will analyze this model in a lot of detail and show a lot of its peculiarities. The first thing to do, and so now I'm taking my favorite quantum field theory book, or you can take your favorite quantum field theory book and you follow the books. What do we do? So the first thing we do, we look at the equation of motion. So this is the equation of motion, you integrate by parts. This is the equation of motion. You put plane wave solutions in, plane wave ansatz, and you find a dispersion relation. That omega squared from the time derivative is px squared times py squared, p being the momenta in the x and y directions. So for generic p, so this is a peculiar dispersion relation, but what we see here is that if py is 0, omega is 0, no matter how large px is. And equivalently, if px is 0, omega is 0, no matter how large py is. This is the hallmark of UVIR mixing. At very low energies, we have sensitivity to very high momentum. Not all high momentum modes contribute at low energies, but there are arbitrarily high momenta that contribute to low energy physics. And this fact is really the key to many of the peculiarities of this model. So this is again the equation of motion, and we'll discuss the spectrum in more detail soon. But I would like to focus first on the symmetries. So this is the equation of motion. I can describe it as a conserved net current. So if we just interpret J0 as D0 phi here, and we call Jxy dx dy phi, then the equation of motion, this equation of motion, can be described as this net current conservation. And if we have a conserved current, we can create a conserved charge, and we can integrate J0 over Y, we can integrate it over X, here at fixed X and here at fixed Y. And they are conserved because if you hit it by d by dt, you put it here, you use the equation of the conservation equation, and then either the dy or the dx is integrated by parts, and we get 0. And the two zero modes of this equation and that equation are tied together, and that's also obvious. So the zero mode Q implements the standard momentum shift. The current is phi dot. So this is the standard thing we call momentum in string theory. And we'll refer to this symmetry as momentum dipole symmetry for reasons that are not obvious from the way I described it here. And it's nothing but the continuum version of the subsystem symmetry on the lattice that I described earlier. How does it act on the fields? It maps phi, these are now continuum fields. It shifts phi of x, y, and t by an arbitrary function of x plus an arbitrary function of y. So this is this huge symmetry. These functions are independent of time, hence this is a global symmetry. But what is peculiar is that these functions of x and of y can be discontinuous functions. Nothing can stop them from being discontinuous. And as a check, you take this free Lagrangian and you perform this shift, then phi dot square is clearly invariant. And this thing is invariant even when alpha of x and this alpha of y are discontinuous functions, because the double derivative kills the discontinuity. So that already tells us that this symmetry is quite special. it's the transformation of the symmetry is separate at each values of x and c, each value of y. There's no continuity in the action of the symmetry. And you will soon see that this is related to the peculiar dispersion relation that we saw earlier. So recall the dispersion relation. And how do we quantize the system? For generic px and py, we solve for omega, and we have a standard Fock space of states, a bit with a peculiar dispersion relation, but this is not that unusual. What's much more interesting is the infinite number of modes with omega equals 0. We can get omega equals 0 either with px equals 0 or with py equals 0. And we have an infinite number of such modes. So let us focus on these modes. They are the interesting modes. So imagine phi, the field, is some continuous function plus a perhaps discontinued function f sub x of x and t and function of y and t. So these are the modes with py equals 0, and these are the modes.
Can I ask a question?
Yes.
Yeah, in your checking the gauge symmetry, you assume that delta x, delta y commutes on the alpha x and alpha y, but if the alphas are discontinuous, then is it a valid assumption? Because delta x acting on alpha x might already give rise to a singularity.
That's a very good question. So first of all, let me correct the question. I did not check the gauge symmetry. It was a global symmetry, not a gauge symmetry. Okay. So that's the first thing I would like to emphasize. But second, if alpha of x jumps, they say a heaviside theta. Imagine there's a heaviside theta function. Theta
yes.
X, there might be a delta function of x. You can take your, this is singular, but when I hit it by d by dy, I get 0. If I have a function of x, no matter how discontinuous it is, the x dy of that function is 0.
Yeah. Okay.
So part of the work here is that we will have these discontinuous functions, and we will have to learn how to deal with them. And a question like the one you raised is a good one. We need to study. And we can also see here, if I take this function and I shift the function of x and a function of y, I can plug it into the action. And even when this function is discontinuous, the action is still finite because the dx dy of this gives 0.
Okay, yes. Yeah, thank you.
So these modes that we shift here can be thought of as the Goldstone modes of the spontaneous breaking of this momentum symmetry. We had a momentum symmetry that shifts phi by an arbitrary function of x. How do we view the Goldstone mode of it? We say, well, we have an arbitrary function of x, and the mode we give it some time dependence, and then we'll have to quantize these modes, right? This is a standard procedure. So one might think that these modes reflect the spontaneous symmetry of the momentum symmetry. We will soon see that this is in fact not the case. We had this subsystem symmetry, this momentum symmetry with discontinuous functions. It looks like the symmetry is spontaneously broken because of these shifts. These are inhomogeneous shifts. But we'll soon see that this is not the case and the symmetry is restored. In fact, it will be restored soon in a very interesting and unusual way. So let's quantize these modes. So I'm just going to take this phi, which is a function of x and t. The 0 mode has to be treated more carefully. We dealt with it more carefully in the paper, but for the purpose of this talk, let's ignore the 0 mode. We substitute it into the Lagrangian. We get a factor of Ly that we just pull out because things are independent of y. And f is a periodic variable, so f is identified with f plus 2 pi. And for every value of x, we have an independent rotor. So this is a problem. For every value of x, we have an independent problem in quantum mechanics of a particle on a circle. This is one of my favorite quantum mechanical systems, a particle on a circle. But now we have an independent such mode at different values of x. In order to get the feel of it better, what do we mean by an integral dx here? We'll tentatively put the system on a lattice. And I emphasize this is not the original two-dimensional lattice. This is only in order to quantize these modes. This is a lattice in a one-dimensional system. So if we put it on the lattice, we just copy in, instead of an integral, we get a sum, but we get a key factor of the lattice spacing outside, which can follow. This is how when we move from an integral to a sum. So now we have a finite number of rotors. When we quantize a rotor, the energy is an integer square. This is the momentum. And the coefficient from here goes to the denominator. So the total energy is sum over x, these are these momentum modes, sum over x n square with the coefficient of order 1 over little a. So as we take the continuum limit, all these states have infinite energy. In other words, classically, we had this shift symmetry, and the fields could be shifted by a function of x plus a function of y. It looks like the symmetry was spontaneously broken, but in fact, this symmetry is not only restored, but all the charge states have energy which is infinite. So we're familiar with symmetries that classically appear to be spontaneously broken, but quantum mechanically they're not. For example, as in the XY model in 1 + 1 dimensions, the U1 symmetry is restored. Here, not only is it restored, it is restored and goes up. The charge state are at infinite energy. This will be quite significant. So how should we interpret these modes, these states? So a conservative approach is that these modes are not really present in the strict continuum limit. They got very high energy, the energy is very high, so these modes disappear from the spectrum. They get very high energy, and we shouldn't discuss them anymore. There's a more ambitious approach which states that the lowest energy state for each charge is captured by the continuum field theory. We have a conserved charge, and if we let n of x have a certain profile as a function of x, and we ask ourselves, what is the spectrum of states with this profile? Then what is the spectrum of states with this profile? Then the spectrum of states will start at energy of order 1 over a, and above that there will be some small fluctuations, and the continuum field theory does take it seriously, and can be analyzed accurately because it captures this universal behavior of the system. So the more conservative approach, and you can take any one of these two. You say these states have infinite energy, we shouldn't discuss them. And the other approach is these states are there, and despite the fact that they have very high energy, since they carry a conserved charge, and this is the lowest state of a given charge sector, this and its small fluctuation, we can analyze it reliably using the continuum field theory. So this is what I wanted to say about these momentum modes. If we look at the current
question, please.
Yes.
Your theory classically looked like it had a whole classical manifold of zero energies solutions, and you've just shown us that all of these are lifted quantum mechanically and lifted sort of infinite energy. So does this mean? So does this mean that this theory will not have this infinite, this Lx, Ly degeneracy that you talked about in your introduction? This large degeneracy.
You're breaking up, so I can't hear every word you said, but we do have the conserved current is there, and it's a good operator, and you can consider correlation functions of it. The Fock space of states with generic Px and generic Py is there, and you can study the spectrum, correlation functions, etc. It's only these subtle modes with Px equals 0, Py equals 0 that are pushed up to very high energy.
Yes.
Modes with small Px are not pushed up.
Yes.
So there's a very subtle orders of limit here, and that's why I was so careful defining the limit. The limit is the size of the system in length units, in centimeters, is held fixed. The lattice spacing going to 0, the number of sites going to infinity. That's the limit we study, and these states are pushed up to infinite energy in this limit. Did I answer your question, Shiraz?
Yes. Will the final spectrum have an infinite, have a large ground state degeneracy?
Well, this is a gapless system, so it's a little bit more subtle, and the answer is no.
Okay.
The strict answer, if you fix the length fixed, then the momentum modes have momentum of order 1 over the length, and they have finite energy. So the ground state in the limit, what is called the strict ground state, does not have an infinite degeneracy in this system.
Great, thanks a lot.
So we discussed this current, and this was this momentum symmetry. But if we have this current, we can also consider a winding symmetry just by swapping which one is 0 and which one is xy. You can check that this equation is satisfied for these two currents. And that's what normally called the winding symmetry. And they're conserved charges, except that the winding symmetry, the winding charge depends on x, and the winding charge, this one, depends on y, and the zero mode is tied together. So this is a very strange winding symmetry. The winding in y at fixed x is a different integer than the winding in y at another value of x, and similarly for y. So that just follows from the current conservation. Now, what are the charge states? Do we or do we not have winding states that are charged under the winding symmetry? So this is a very interesting configuration in our continuum field theory. Theta is the Heaviside theta function. X and y are within the fundamental domain of length Lx and Ly. And you can check that this configuration is continuous on the lattice, because it's periodic on the lattice. Because if we shift x by Lx, because of this phi, it is shifted by a Heaviside theta function in y. And if we shift by y, it's a Heaviside theta function in x, but the coefficient is 2 pi, and phi is 2 pi periodic. So this is a good configuration. It is a periodic configuration on the lattice. So by our rules, we should study it. And if we substitute this configuration in the formulas for the charges, we see that this configuration has winding, in fact, there's a delta function in x if we integrate dy, and it has a delta function in y if we integrate dx. So this configuration is charged under the winding symmetry. At generic x, it doesn't wind, but at x equals x0, it has winding 1 if you wish, because of this delta function. However, these configurations have infinite action. They have infinite action because in the action, we have this term, dx dy phi. So if we just substitute it in here, we get the argument of the square is linear in delta functions. And when we square it and integrate, we're going to get a delta of 0, which, if you think that there's an underlying lattice, should be interpreted as 1 over a, the lattice basic. How should we interpret such configurations? Do we or do we not have such winding configurations? And we have two approaches. The conservative approach says that such configurations and the corresponding states are not in the continuum limit, because all the charged states under the winding symmetry have energy of order 1 over a. And the conservative person would say, oh, they have very high energy, then I don't care about them. A more ambitious approach says that these configurations and states carry a conserved charge. And although this charge is not present on the lattice, the underlying lattice model does not have a winding symmetry, these states do carry the charge, and as such, maybe we should study them. In fact, you can check that the lattice violates the symmetry, the winding symmetry, at energy of order 1 over a squared. And these states have energy of order 1 over a. So although they have very high energy, it's parametrically much lower than the energy at which the winding symmetry is violated. And therefore, it is meaningful to discuss the symmetry in the charged states. And furthermore, the behavior of these states and small fluctuations around them, since these are the lowest states carrying a conserved charge, is captured universally by the continuum field theory. I would like to summarize the kinds of fields we study and its configuration and its the singularities. So on the lattice at every site, the field has 2 pi periodicity separately at each site. In the continuum limit instead, we only knew that the plaquette has to be much less than 1, because that's what the continuum pushed us to. So if phi is not necessarily small in the continuum, it has a 2 pi periodicity. It has therefore a 2 pi ambiguity. So we cannot assign a real value to phi, because phi and phi plus 2 pi are identified. And therefore phi is not a good operator, but e to the I phi is a well-defined operator. This is completely standard for a compact boson. In the compact boson, if phi is not a good operator, e to the I phi is, because phi has a 2 pi ambiguity. In our case, the x derivative of phi and the second x derivatives are also not small. the plaquette has to be small, but if you have only x derivative, phi at one point and phi at another point might not be near each other. And therefore, they're also not well-defined operator. But dx dy phi is well-defined because it's small. So dx dy phi does not have the 2 pi ambiguity. And since it does not have the 2 pi ambiguity, it is a meaningful operator. And we have a hierarchy of cases. If the plaquette is of order a square, look at this equation. If the plaquette is order a square, then the second derivative is finite. That's clearly included in the continuum field theory. But if the plaquette is of order a, dx dy phi is still meaningful because it's parametrically smaller than, it does not have the 2 pi ambiguity. And this is the case we discussed earlier where we have a single delta function but no double delta function. So excluding these configurations was the more conservative approach I said before. It is a valid approach, but it's more conservative, and a more interesting one takes them into account. We can state this fact also slightly differently as a gauge principle. On the lattice, phi is totally discontinuous, and at every point x and y on the lattice, we have an ambiguity by shifting by 2 pi. And this is an arbitrary function of x and y, which can jump around different integers at different points. In the standard compact bosons, which is the standard extreme, we have only an overall 2 pi ambiguity in phi. The derivative of phi is good, and therefore there's only an overall 2 pi ambiguity. In our case, phi is identified with phi plus 2 pi times an integer that depends on x plus another integer that depends on y. So we have this gauge principle of phi is in between the gauge principle in the lattice and in the continuum. Just as the fields we have are in between the totally discontinuous functions on the lattice and the continuous functions in the standard case. And what it means in terms of symmetry is that we said before that we had this symmetry that shifts in x and shifts in y by a real number, but now we see that these alpha of x and alpha of y are really in u1 rather than x. So not only can they jump from point to point, they are circle valued, these functions. So the function is u1. Now, at this point, this story might sound familiar, especially to the string theorists among you. And this system enjoys a t-duality. We can take the phi field and define another field, phi tilde, through these equations, dx dy phi. So phi mapped to phi tilde with extended t-duality transformation. And you can check that the full theory is invariant under this duality. In fact, even the momentum symmetries and the winding symmetries are exchanged under this symmetry in the states of order 1 over a, which are not strictly in the continuum limit, and I've had a whole discussion whether we should really take them seriously or not. These states are have energy of order 1 over a, and yet they are mapped correctly under this t-duality. So this whole thing is very reminiscent of the compact boson, standard compact boson in 1+1 dimensions. The momentum symmetry and the winding symmetry, there are these momentum and winding symmetries. They are unbroken. T-duality exchanges them. The main thing here is that when the dust settles, all the states that are charged under momentum and winding have very high energy rather than low energy. This has an interesting consequence in what we call robustness. So our continuum theory on the lattice has momentum and winding, but on the lattice we have only the momentum symmetry. So this motivates a question, which is very important, say, especially in condensed matter physics, is this whole story robust? A quantum field theorist or a string theorist would say that for a compact boson in 1+1 dimensions, the system makes sense and it's gapless and it's a conformal field theory. And it has t-duality for any value of the radius, and momentum and winding are good symmetries and they are exchanged. If you come from the lattice, you would say this is true above the Kosterlitz-Taulich point, but at lower point, for lower radii, for smaller radii, the system is not robust because an operator like e to the I phi tilde, the lowest dimension winding state, is relevant below the Kosterlitz-Taulich point. And since it's relevant, and since on the lattice we didn't have that symmetry, in the continuum we should also turn this operator on. And as we turn it on, it gaps the system, it completely ruins the story. The high energy perspective state, yes, as long as we go a little bit outside the Kosterlitz style, if not by an infinite amount, but by a finite amount, there's only a finite number of such relevant winding states. We tune their coefficients to 0, then the symmetry is there, and then we can proceed. This is what we normally do. In our case, we don't even need to do that, because the operators like e to the I phi tilde are irrelevant. In fact, they are very, very irrelevant, because this operator that creates a winding mode, or its T-dual, which creates a momentum mode, when it acts on all the low energy states, it creates a state charged under the momentum and winding symmetry. And in our limit, all these states have very high energy. So even if you perturb the system on the lattice a little bit, by violating even its momentum symmetry, the system remains robust at low energies. So far, I'm about a little bit beyond half my talk. I described this phi system, this matter system. It doesn't actually have fractons, but it's gapless, and it has all these peculiarities with discontinuous fields. I'll start rushing now because I have lack of time, but I would like to give you a feel of what the gauge theories of these systems look like. So
sorry, just
yes.
one question before you move on. So I just wanted to understand, like roughly how many states are there. So if I calculate the partition function at some finite temperature or turning on chemical potential for these charges, do they exist?
If you turn on whatever is charged under the charges, if you put chemical potential, all the states that carry charge do not contribute to the partition function when you sum over in the continuum limit.
Okay, so
you can go you can be a little bit more sophisticated and subtract. So focus only on particular charge.
Mm-hmm.
And then there would be a shift in the energy. And modulo this finite shift, you will get a universal answer.
In all the charge sectors, there is a universal answer. The same answer you get in every charge sector, is that?
That's correct. So if you fix the charge, which was this n of x, and you consider small fluctuation around this point, this is universal. That's easy to check because it comes from this Lagrangian. And if you put, the way to check is you add higher order terms to the Lagrangian and see whether they mess up your answer. And it's easy to check that they don't.
Okay. And what about temperature? If I add a temperature, which is small.
Same thing. I described the Hilbert space. See, this is a free theory. In the end of the day, the theory is free. So I give a complete description of the Hilbert space. And if you want to compute the trace with the temperature, then be my guest. It's not going to change that. In the paper, we also studied some two-point functions, some correlation functions, and how these states, these funny states, enter in the correlation functions, and how the various limits don't commute affect the correlation function.
Sorry, just one more question. So this free energy, if I calculate, how will it scale with the length scale, this L?
I have not calculated the free energy, but it's completely straightforward because if you take the strict continuum limit, so A goes to infinity, all the states that are charged are not there. You have to sum of the momentum, so Px and Py are quantized in units of 1 over Lx and 1 over Ly. So you have a double sum, and for every one of them, you have e to the minus, etc. The standard Fock space computation.
Okay, thanks.
Sorry, Nati, this is totally obvious, but I just want to make sure I understand it properly. Besides the term you wrote down, which had 4 spatial derivatives, if I were doing very naive power counting, I would have, of course, written down the standard 2 derivative terms involving spatial derivatives. And your point is that if you impose the symmetries you were imposing, phi goes to alpha of x plus beta of y types, then those terms are ruled out, perhaps, but not the ones you're keeping. So it's a natural thing to do, in the way we think about in particle physics to not. Okay.
Yes, this is exactly right. This is a very good comment. The high energy physicists would say you impose a global symmetry, you write all the terms that violate the symmetry are excluded, you analyze the system. Once you're done doing that, you can start exploring various perturbations and ask what happens when you explore these perturbations.
Yeah,
okay.
And Nati,
Yes,
Rajesh here. So sort of
Oh,
a
my
similar
friend.
question. Hello. Yeah, a similar question, a little bit perhaps stupid, but so the when you took the continuum limit, you dropped the lattice theory was an interacting theory. It had this cosine phi, and then you dropped the interaction terms when you sort of took the naive continuum limit. But now in your ambitious approach where you're keeping some terms which scale as 1 over a to various powers, are the interaction terms irrelevant even when you do that scaling?
Absolutely, yes. That's crucial. This is an excellent point. If you expand the cosine, the argument of the cosine had a squared times the double derivative. So when you expand it, it starts at order a to the fourth. And so you really need to do the whole thing more carefully with the powers of a. But these states at order 1 over a are still captured universally, even if you expand the action to higher order.
Okay, thanks.
And the underlying principle is what Sandeep said. There's a symmetry that controls it. So there are high order corrections, but because of the symmetry, what we extract out is the leading order term. So I'd like to briefly discuss a gauge theory of this system. I do not know how far I can get in my talk, but please ask me questions. There's huge literature that can be phrased as tensor gauge theory. It's mostly in 3+1 dimensions, but I'll speak to 2+1 dimensions. And most of the literature is in a Hamiltonian formalism and for Zn, and I'll stick here to U1, and since it's mostly in a Hamiltonian formalism, I will do it in a Lagrangian formulation here. So we have a Euclidean lattice, we have time-like links, we put U1 phases on the time-like links, but on the space, instead of putting the variables on the links, we put the variables on the plaquettes. So we have a two-dimensional spatial lattice with the degrees of freedom on the plaquettes, and we add in the time direction, we add a lattice, and we put we put phases also on these links. And the interactions are products of all these U's around the cube, around the space-time cube. And the gauge symmetry is at the sites. So at every point here, and it multiplies this plaquette and all the plaquettes and the links that touch the site. And you can check that this product of the cube is indeed gauge invariant. So this is straightforward. Let's write the continuum Lagrangian for it. So we'll have two gauge fields, A0 in the time direction and AXY in the space direction. And we have a gauge symmetry. A0 goes to A0 plus D0 alpha, and AXY goes to AXY plus DX2Y alpha. And we can form an invariant electric field. And there's no magnetic field in 2+1 dimension. You can check that this is gauge invariant. And this whole gauging can be thought of in continuum language as the gauging of the global symmetry we discussed earlier in the scalar field theory. When we had a scalar field theory, it has a global symmetry. Now we say, forget where it came from. We have this global symmetry. Let's write a gauge theory for that particular symmetry. So this is the gauge theory that we write down. But now we are very interested in the global aspects of the gauge symmetry. So we ask ourselves, what is the flux quantization? Now, globally, this alpha that we discussed, the gauge parameter, is subject to the same identification as the phi that we discussed earlier. So alpha is 2 pi periodic, and what we mean by that is alpha is identified with alpha plus 2 pi times an integer valued function of x plus an integer valued function of y. And since we allow such alpha gauge configurations, we should also allow large gauge transformation. So this would be a large gauge transformation. It is periodic on our lattice, in our continuum system. It's periodic on our torus, but it's not continuous because of all these jumps, because of the theta functions. And if we allow such gauge transformation, we can also consider such an alpha for the transition function as we consider the system on the Euclidean torus. I'm basically imitating what we do in the U1 gauge theory. The novelty is that we allow such alphas that are discontinuous, and that have these identifications with an integer, and therefore we allow such discontinuous alphas. And just from the twisted boundary conditions, we learned that the fluxes are quantized. The electric field on x and tau can be a delta function of y, and the electric field in y and tau can be a delta function of x. So this is just the space of configurations we studied. Now we would like to ask what's the Lagrangian and analyze the system. So we can put the electric field square, and because of the...
May I ask the question, please?
Yeah.
Yeah. So when you write integration over d tau with a circle, so how do you complete the loop? So you go around the placket, or?
So first of all, I no longer have plaquettes. I'm in the continuum. I switch from the... I presented the system...
Oh, I see. Okay, thank you. Yes. Okay.
So because of the flux quantization, theta is 2 pi periodic. And how do we analyze the system? So that's again, we follow your favorite textbook. We choose an A0 equals 0 gauge. Then we have Gauss law, the x dy of E equals 0. And then we solve Gauss law, and we learn that AXY, I put factors of the length here for later convenience. It's a function of x and t plus a function of y of t. So even before analyzing it too carefully, we immediately see that this system has no local excitation. Once we picked A0 equals 0 gauge and we impose Gauss law, there are no local excitation. We'll work out the spectrum soon. So this whole story is very reminiscent of ordinary U1 gauge theory in 1 plus 1 dimension. So earlier we discussed the SPI system, and although being in 2 plus 1 dimensions, and it has all these peculiarities, it was in many ways similar to an ordinary scalar field theory in 1 plus 1 dimension. Now we see that the corresponding gauge theory, U1 gauge theory, is similar to a U1 gauge theory in 1 plus 1 dimension. It has an electric field square, it has no magnetic field, it has a theta parameter, and it has no local excitation. In the ordinary U1 gauge theory in 1 plus 1 dimensions, we are left only with the holonomy around the circle, 1 quantum mechanical degree of freedom, the holonomy around the circle. And in this case, we do have that holonomy, but we have a separate holonomy. We are in 2 plus 1 dimension, a separate holonomy for different x's and a separate holonomy for different y's. So in that sense, this system is very similar to the U1 plus 1 dimensional system. Let me say a few words about the defects of the system. So Sandeep asked me earlier, where are the excitations? So this system on the lattice has excitation. In the continuum, it does not have any excitation, very much like lattice gauge theory compared with continuum gauge theory. It has no charged excitation, but we can capture them with defects. And the simplest defect is an integral over time of A0, and it represents the wall line of the particle, fixed position. But since we don't have AX or AY, this gauge invariant defect cannot be deflected. It is stuck at one point. So this particle, this pro-particle, is a fractal. We can also have a dipole, particle with charge 1 and another one with charge -1, separated in x. And then using this AXY, we can let this dipole move in y, but it cannot move in x. So the gauge invariant of the system leads to the restricted mobility. So the restricted mobility of probe excitations follows from the underlying gauge symmetry. So I managed to capture something that is common in the fractal literature, but here I state it, since I only look at the low energy theory, I state it as a property of the defects. Let's work out the operators in this system. The operators are normally a Wilson line, which don't go in time. Wilson line in time is a defect, a Wilson line in space is an operator. Here these are Wilson strips. If we integrate dy around the circle, so that's gauge invariant, and then we need some width in x. These are the operators. And we have point operators, which are the electric field. But Gauss law says that the x and y dependence of the electric field is relatively simple. And these two operators do not commute with each other. Let me finally work out the spectrum. We said that after we choose time like a temporal gauge, and we impose Gauss law, we can restrict A to be of this form. So again, ignoring the common zero mode, we plug it into the Lagrangian. We still need to quantize these modes. And this is the effective Lagrangian of these modes. In the large gauge transformation, the same large gauge transformation that I mentioned earlier identifies f not with f plus 2 pi, but with 2 pi times a delta function. In fact, this delta function can be seen that it has to be there just by using the dimensional analysis. So we still have an infinite number of rollers, very much like in the previous problem. We have an infinite number of rollers, one per each x. But if before we had a 2 pi periodicity without the delta function, and as a result, we got spectrum that goes to very high energies, now the periodicity of the rotor is infinite. It's of order 1 over A. And as a result, the spectrum is finite. So this is the formula for the spectrum. We have integers from quantizing the rotor, theta from the standard theta term, squared, sum over a lattice, but we still have one coefficient power of the lattice spacing out front, now in the numerator. And as a result, all these systems, all these states have very, very low energy. So this is unlike the system we had before. Here we have a system with no local excitation, an infinite ground state degeneracy, and an infinite ground state degeneracy, and a fractonic-like excitations in the sense that they are restricted. Now, I plan to give a discussion of ZN gauge theory of the same system, but basically,
sorry,
yes.
You describe fractons as defects of this theory. Are they part of the Hilbert space also?
They are not. They are not part of the Hilbert space of the continuum theory. They are part of the.
Even if you look at sufficiently high energies?
They are. It's just, imagine you study a U1 gauge theory, say in 4 dimensions. Is there an electron in the system? No, there isn't. You solve the U1 gauge theory in a. You solve for the U1 gauge theory in 4 dimensions, the photon. This is in your first semester of quantum field theory. There's a spectrum. There are no electrons in the spectrum. There are no charge excitation. Can you check the leading order effect of very, very heavy electrons? Yes. All you have to do is study Wilson lines in that gauge theory.
I see. So if this gauge theory is to be thought of as, so can I think of coupling this gauge theory to the previous theory that you talked about?
Yes.
Because global symmetry.
Absolutely. Then you will have it, both the gauge theory and the electric excitation, and you can
those
actually
would be fractonic.
And then you can actually make it more interesting by saying that this phi that we discussed before is charge n, not charge 1, but charge n, and then it can Higgs the U1 to Zn. And there might or might not be various heavy excitations. The point here is that we try to describe only the low energy theory. We try to zoom on the low energy theory and study only that and see what we can say only in the low energy theory. What's the universal behavior at low energy? Now, we can make the model more complicated. We can add various scalar fields, transforming linearly and non-linearly. We can do it on the lattice. We can do it in the continuum. Every one of these things can be done. I wanted here the absolute minimum continuum theory that captures the low energy behavior of the lattice model. So that's what I wanted. And you see and learn what's new. And what's new was the new stuff in this continuum theory are these discontinuous fields, these peculiar global and gauge symmetries where charges change discontinuously, and now we see fractonic excitation.
Okay, thank you.
Now, the next few slides, I'm going to skip them. They were about analyzing precisely this Zn gauge theory. I'm out of time, so I decided I'll skip a little bit this Zn discussion and say what happens in 3+1 dimension. So in 3+1 dimensions, many of the ingredients of what I said before, including what I said about the Zn gauge theory, are still true. We have discontinuous fields and we have exotic symmetry, but the symmetry is a little bit more complicated. We don't have just Z4 rotation by 90 degrees. but we have the symmetry group of the cube, which is a non-abelian group, and we have more indices because the rotation group is non-abelian. Just as in 3+1 dimensions, the standard rotation group is SO3 as opposed to SO2, which is abelian. And we studied various theories. We studied a theory similar to the pi theory that we discussed here. So it's similar to the discussion in 2+1 dimension, except that it's not self-dual as here, but it is dual to an exotic U1 gauge theory, which we call A hat theory. It's again one of these theories that has a very peculiar exotic global symmetry that we gauged. So the gauge symmetry is peculiar. And again, there's flux quantization, etc. And this system is dual to the pi theory. Similarly, there's a U1 gauge theory, similar to the discussion that we had here, except that now it is dual to a non-gauge theory, which we call phi hat theory. So we analyzed these in detail in the paper. And the part that I skipped here about the ZN gauge theory, we did it also in 3+1 dimension, and we found 3 dual descriptions of an exotic gauge theory. And it's similar to the discussion I did not do here. We either Higgs the A theory, this gauge theory, by this phi, or we Higgs this A hat gauge theory by this phi hat, or we can dualize it and find a BF type description involving the gauge field from here and the gauge field from here. And these 3 continuum descriptions give us dual descriptions, and they capture the low energy theory of some various lattice models. And it turns out that this is not any random lattice model. This is one of the most celebrated Fracton models. It's called the XQ model. It's for Vj high U. So this is a continuum field theory that captures this model, and it captures all its peculiarities. It captures the ground, its gap. It captures its ground state degeneracy. It captures all the fractonic excitations, and it is robust. So this is unlike the 2+1 dimensional ZN gauge theory, which I did not discuss. So this whole thing is done in 2 other papers, and I'm already way out of time. So let me summarize. Fractons, it's a huge subject. There are many papers in the condensed matter and quantum information literature. And they exhibit interesting properties which seem incompatible with the framework of continuum field theory. That was clear even long before we stepped in. And we presented non-standard continuum field theory. We tried to bend the rules as little as possible so as to accommodate these fractons. And there were 3 ingredients. All of them I emphasized are essentially unavoidable. First of all, invariant only under discrete rotations. That's not very bothersome. We have continuous space in the continuum theory, but the field theory, the continuum field theory, still remembers the orientation of the underlying lattice. That's not that shocking. We had these exotic global and gauge symmetries, but this is perhaps the most interesting thing, is that we studied also fields in our continuum field theory and gauge transformation parameters that are discontinuous and even singular. They are less singular and less discontinuous than on the lattice. And in that sense, we capture, we have fewer configurations than on the lattice, but they are more discontinuous than allowed normally in the standard continuum field theory. And the claim to fame of these theories that we have, these 11 different theories, is that they capture the universal properties of the underlying lattice system. And they reproduce the long distance physics and the properties of probe particles, as I emphasized here in the example. So again, I described here only 2 examples, this pi theory and the U1 gauge theory. Altogether, we studied 11 different models. There's a huge outlook, and there's a lot that can be done. One question that I think really begs an answer is to find a more coherent treatment of this discontinuous field, something that the mathematicians would be pleased with, rather than the way we function is that we made up the rules as we went along. So we took derivatives. Somebody asked me, is it meaningful or not? And yes, we took the x, the y derivative of the discontinuous function of x. This whole thing has to be stated much more precisely. And that made its way into these gauge theories with these twisted bundles and these bundles with this large gauge transformations and the flux quantization. I feel that there must be a much better treatment of that, understanding the geometry of these gauge fields. We limited ourselves to flat space. In the fractal literature, there's some discussion about curved space, how to put these systems on curved space. I personally feel that finding a continuum description is the first step towards placing the system on more complicated manifolds, say with a curvature, and maybe even have non-trivial global aspects of it. There are many other models, lattice models that people studied, and we would like to fit them into our framework. I'm working with a number of postdocs and my 2 students, and kind of going through the literature of such models, trying to fit them into our framework. And honestly, it's really very, very exciting, partly because I have these fantastic collaborators. And what perhaps is the most interesting thing is to find more such models and to put order in all these models. So I apologize for going over time, so I'll stop here. Thank you and stay healthy.
Thank you very much. I would like to request everyone to unmute and thank Nati by clapping. Questions?
Sorry, maybe I can ask a really stupid question if you'll permit. Nati, I'm very sorry. I think I understood at least a little bit of the first part of the talk where you were doing the analog of the XY model, but I got increasingly lost when you went to the gauge theory.
So, I apologize about that. I think it happened because I went way too fast.
No, but just to ask you, the fractons referred to then the excitations in the gauge theory, was it? I'm sorry to ask you.
No, they're not the excitation of the gauge theory. Okay. So in the phi system, there was a global symmetry, yes, and there were excitations of the Lagrangian that carry charge under the global symmetry.
Yes.
In the gauge theory, there is also a global symmetry that I didn't discuss, but the charge, quote unquote, excitations are not excitations of the system. They carry gauge charge, not global charge.
Okay.
The continuum Lagrangian does not have them as dynamical excitation. Instead, you could ask, how can we think about them? We think about them in terms of Wilson lines. So you can think of QED in the following way. At very low energies, we have only F mu nu squared, no electron. So you analyze this 6 thing, that you do that in the first class of quantum field theory. Then what about the electron? So if you're very, very sophisticated, you add fermion fields and you quantize it and there are interactions and perturbation theory. But if the electron is very heavy, in the limit that the mass of the electron is very high, you don't need all that. Instead, you take a Wilson line for the electron and another Wilson line for the electron, and you compute the correlation functions of these. So that's the low energy perspective of QED. So what I presented here, and also in the papers in all the other models, is the analog of that. Namely, there is a low energy gauge theory. There are no excitations of the low energy field theory that carry gauge charges, but the physics of such would-be charged particles or probe particles is captured by these defects. So it's completely analogous to what you normally do, and it's more universal, because if you do QED, the answers will depend on the mass, and you might want to add quantum interactions, and there might also be a charge scalar field, and there could be all sorts of other massive things that contaminate the answer. Or if you really go to high energies, then that's the answer. But if you're a low energy person, they contaminate the answer. Whereas in the limit, if all these modes go to infinity, the low energy free field theory with defects capture the relevant information with all that. So this is very similar. So in that sense, the low energy field theory here in all the examples that we studied, 11 models, the low energy field theory is a free field theory, and it's straightforward to analyze. It could be subtle because of all these factors of A and the question of what's universal and what's not, and which defects are allowed and what are the properties of the defect. It's subtle, but it is straightforward. You don't need to crazy ideas. You just follow your nose and do what you're instructed to do.
Natty, if I can pursue along these lines, so one way to, as you said, in quantum electrodynamics, to have an electron is to just either think of a defect in the electromagnetic Lagrangian or add an electronic field, which would be analogous to coupling the two systems. The first matter theory that you talked about, which had a particular global symmetry, which was the same as the gauge symmetry that we later discussed. So there, I would imagine the charged excitations, which had infinite energy, would serve as these defect particles of the gauge.
No.
Gauge
The charged excitations were charged, well, yes and no. If you just, there's a question of range of parameters. If you just take the scalar field theory as I wrote it, and couple it to the gauge theory as I wrote it, in that range of parameters, classically, the gauge theory is classically in the phi system, the global symmetry was spontaneously broken. And correspondingly, if you couple the two systems, the U1 gauge theory is fixed. It's a totally different limit. This is what you normally do in 2 dimensions, in the XY model or in the compact scalar field. The momentum and winding symmetries are restored. But if you couple the momentum symmetry to A, then what you write d mu phi plus A mu quantity squared. And in that limit, A mu is fixed and the whole thing is gapped. So you can construct, you can add massive particles that transform under that symmetry. It's not a, so the field would be the e to the, what I call phi, the field in this theory would be e to the I phi. You can write kinetic term. This would be another system.
Okay.
So you can write many different Lagrangian, and every Lagrangian does its own thing, but they have to be analyzed from scratch. I really want to emphasize that these 3 ingredients, the fact that we don't have rotation symmetry, the peculiar symmetries, and the discontinuous fields are not impossible to analyze, but every single thing that you're familiar with and you're used to needs to be rethought. It's not impossible. You just go carefully through what you normally do and check whether everything is still correct, but it needs to be done. So you cannot just copy answers.
I have one. Sorry, Shiraz, go ahead.
No, go on, Spencer.
Natty, I have one small question. I mean, your gauge field is dynamical, the one that you introduced.
Yes.
Is dynamical. So I was just wondering, in terms of the usual XY model, in which, in order to take into account periodicity in the continuum limit, you introduce a fictitious gauge field, and then you do this Poisson summation formula and arrive at a model involving magnetic vortices, etc. And there, of course, I have a very nice way of understanding the Kostelis-Thouless phase transition, actually. Is there some Kostelis-Thouless transition in this type of model? If you have a gauge field which is dynamic.
Your question is really about, if I understand correctly, your question is about the phi system, the first part of the talk. No gauge fields, just the phi system. And the way you perform the duality, you can do it both on the lattice, this is Kramer-Venier duality, or in the continuum, the way you normally do T-duality in the continuum. Both things work for this model. In fact, for the analog of Kramer-Venier duality has already been done by others before us. The continuum version of the analog of T-duality is what we did. But the main difference between that and the 1+1 dimensional system that you mentioned is that in the continuum theory, the way we define continuum, there is no Kostelis-Thouless transition in this system. And the reason is, as I said, that all the momentum charge, all the states charged under the momentum and winding symmetry have infinite energy. So if you act on the vacuum with the charge, with the operator that tries to create them, it takes you, it has matrix, it does not have diagonal matrix elements in the low energy theory. It does not have matrix elements within the low energy theory. It takes you to states of order 1 over A, which are very heavy. And as a result, these operators are very, very irrelevant. So, but many things are the same and crucial things are not the same. So this is the same thing I said before. It's a lot of fun because you go carefully through all the things you know, and you just check one after the other. Is it the same or is it different? And we landed on a coherent story, rather surprisingly.
Okay. Thank you.
You mentioned right at the beginning that there is this UV-IR mixing in some of these theories. Now, I knew,
Shiraz, I knew you would love this thing. This was there just for you.
The gauge theories you talked about have this dense spectrum of very low energy states whose details depended on your latticization. Is that I suppose is one of the manifestations of this UV-IR mixing?
Right. So, yes, so in the gauge theory that I described, and also in other gauge theories that I did not describe, there is an infinite ground state degeneracy. There are no local excitation, but there's an infinite ground state degeneracy. And the infinite ground state degeneracy is such, exactly as I said before, that these are modes which in some sense have px equals 0, but arbitrarily large py. This is the UV-IR mixing. Or py equals 0 and arbitrarily large px. Let me go back to this formula. So it's this formula. So in the limit a going to 0, the states are labeled by an integer valued function of x and an integer valued function of y. And the function at nearby points has nothing to do with each other. N at x and n at x plus epsilon are totally independent integers. This is the spectrum. So this is the UV-IR mixing. It's IR in the sense that it is at low energy. It is IR in the sense that there is no y dependence here. But it's UV in the sense that this momentum can be could be different at different values of x.
And did the phi system that you talked about at the beginning, did that have any UV-IR mixing?
In the end of the day, it does not. In the phi system, it does not, because instead of having A here, we had 1 over A. So in the end of the day, all these states really decoupled. Having said that, this is what happens in the limited twist study. A going to 0, fixed size. This is what you would normally call continuum limit. You hold the size of the system in centimeters fixed, and you send A to 0. If instead you send, let me go back to the formula and you will see it there. This is the formula for the energy. So we have the same nx squared that depends on x as before. And we have here 1 over a times ly. So as a goes to 0, this is the limit I discussed. L fixed, the length fixed, a going to 0, this whole spectrum goes up to infinity. But you might want to say, no, I don't want to study this limit. I want the lattice spacing fixed, and I want the number of sites going to infinity. I want the number of sites going to infinity. If the number of sites goes to infinity, it means that this Ly goes to infinity. And then all these states come down. So depending on how you take the thermodynamic limit and the continuum limit, in which order you take the limits, these states are at 0 energies or are at infinite energies. So this is another manifestation of the UV-IR mix. All this is just to say that even though these theories are free and are really straightforward to analyze, you really have to be careful about all these subtleties. And I think that in other systems that are more sophisticated and more elaborate, there would be even more such subtleties.
Thanks a lot.
Nati, so you mentioned the systems you studied. If I understood, they all the low energy description is always free. But you can, this is if you started from the lattice models, you mentioned 11 of them. But if you were to just take look at the class of theories which have exotic symmetries of this generic kind and without necessarily having any other spatial symmetry, etc. You could imagine discussing, writing down interacting theories with, will they have some peculiar features which because you would think that with discontinuous fields and so on, the interacting theories will be sick in some way, or will be kind of
maybe they will be sick, maybe they will not, but they have an answer. Right?
Yeah.
So we started from something that manifestly makes sense on the lattice.
Yes.
You can add more interactions on the lattice and take the limit, and either you can capture the answer in the continuum field theory or you cannot. So this was our starting point. There are systems that are completely well defined. There's nothing sick about them. They exist, and you can solve them numerically or whatever, and they give an answer. I picked here one example which highlights some of the peculiarities. This example is free. It's true that all the examples we studied are free in the continuum limit. And for all we know, there are other examples which are not free in the continuum limit. There might also be other examples that cannot be fit into such a framework. But I don't think there would be any example which is really sick, because we started from a meaningful system. We started from a system on the lattice, which was completely finite number of degrees of freedom, compact target space. There's no room for unitary Hermitian Hamiltonian, unitary evolution, all the nice things we like. And then, so it does make sense. And then you can ask, the question I asked here, that we asked ourselves is, can we fit the low energy behavior of this completely well-defined system into the system that we love so much of continuum field theory? That's the question. So I don't think this will give something sick. It would either give us something like the ones we discussed, or maybe I'll need to throw in more elements we have not yet discussed, or it will have some interactions, or perhaps it cannot be fit into this framework of quantum field theory. But getting a sick answer, that I don't think can happen. Because we started with something.
Yeah. No, if we forgot about the lattice origin, of course, that's a very good way to get healthy theories by taking the continuum limit. But if one just focused on the space of theories in this enlarged continuum field theory, it would be interesting to see if there are, if you relax it in the ways that you did, whether there are.
So the first thing we need to understand is this thing. We'd like to make this treatment of the discontinuous fields more precise. And then this will tell us how to add more terms, which terms are allowed, which terms are not allowed. How can we treat that? And I do not know the answer to that. So you're asking an excellent question. You said, let me rephrase. If you start from a healthy lattice system, you're going to end up with a healthy system, which you might or might not be able to describe using this continuum language. Then after a while, you could ask, throw away the lattice. What is the space of continuum theories like that I can write down? And I clearly don't know the answer. And it might be that some of them are sick and others are not. There could be all sorts of restrictions on the kind of terms I'm allowed to write down. We know that very well. There are continuum field theories which are healthy. There are continuum field theories that are sick. For example, they might have anomalies, or we might have these, say, co-derivative terms which have the wrong sign. So there are all sorts of restrictions that need to be imposed. And people have been studying that in the context of standard continuum field theory. Here we haven't done it yet. We have not even finished analyzing all the free field theories in this form. And, I'm studying a whole bunch of models that I didn't discuss here with these excellent students and postdocs that I'm interacting with. And all this was done, of course, with Shuheng Shao, who is excellent. But they still exhibit new peculiarities as we go along. So I feel that this is kind of mostly unexplored territory. We should first study the free theories, and then we study the interaction and try to formulate it better, et cetera, et cetera. just as you said. There's no guarantee that it would work. It might also be probably misguided because maybe we shouldn't try and force all these systems into the language of continuum filter. Maybe that's the right answer. But we will not know until we try.
Okay, thanks. A quick second question, which is that do you have any speculations or any things of whether these more general continuum theories could have some string theory realization in terms of some D-brain constructions or something?
So, but the answer is, well, there are some continuum, some of these systems can be described as a stack of standard quantum field theories. So take quantum field theories saying X, Y, and time, and you take a family of them labeled by Z, and you stack them together. And then you take another stack in the XZ direction, and you stack them in Y. Then you take another stack in the other direction. And some of these peculiar fractal models have this property, and then the restricted mobility is clear because they really live in one of these field theories, not the other. And some people propose that maybe we should study D-brains like that, take a very dense set of D-brains. But we really need an infinite number of D-brains to really get a continuum description. So that's how it might fit. I have not thought about it in detail.
Thanks a lot. Great talk, Matthew.
May I ask a small question?
There is a question. There is a hand raised.
A small one. So if I remember, this AXY that you wrote down was a symmetric in X and Y.
Which one?
AXY, the gauge field.
Yes.
And so it is not associated to a differential two form on anything. So what kind of anomaly do you expect from these theories?
Okay, so first of all, it's not a form because it is quadratic. It is symmetric in X and Y. Not an anti-symmetric.
Exactly. So it's not a two form.
It's not a two form, and I do not know a more geometric way of saying it. In fact, this was in the Outlook slide that I showed here. Understand better the underlying geometry of these gauge fields. So your question is really, how do I understand it better? And I do not know the answer, but what I do know is that they have a very standard description on the lattice. It is a very standard continuum way of writing it, which is what I had in the slide. Neither of these is mine. I was not the first one to write it down, both in 2+1 and in 3+1 dimensions. This is the structure. The thing we did add in the continuum is the global structure, the quantized fluxes.
So I won't be able to associate a field strength with this.
Sorry.
So I won't be able to associate a field strength to this form. So this field. Is that right?
Here it is. This is the field strength. You can check the.
Oh, I see. Okay. So in this way.
Yeah. And if you go to 3+1 dimensions, there are electric fields and magnetic.
Yes.
We don't deserve any credit for this. This was done earlier, and I tried to give some references to the early papers here. And there's really a very large literature of such gauge theories.
I see.
Both on the lattice and in the continuum. But what we added was the more careful description of the global structure and the classification of the defects and connecting that to what's being done in other systems.
Yeah, but D-brains typically associate to antisymmetric tensors.
Yes, it's not the same thing.
Yeah.
Sorry, maybe there is the next question here.
Yeah.
Maybe you can.
Thank you.
Ask the question.
Welcome.
Hello.
Yes, please.
Can you hear me?
Yes.
Yeah. Actually, I see the dispersion relation, and it can have a scaling symmetry, which is Lipschitz-like scaling symmetry. a non-relativistic theory.
There's some static, so I can't hear you.
Oh, you. Hello.
Yes, I can hear you now. I can't hear you. I'm sorry.
Oh.
No sound is coming. No, cannot hear it at all. Okay, Loga, you want to ask your question?
Okay, maybe I can ask. I think you can't hear me. Is there ellipsis scaling invariance in your theories?
There is scale symmetry, not on the lattice. On the lattice, there's never a scale symmetry. In the continuum, there is a scale symmetry. And there is scale
continuum.
Symmetry. Yeah. So in the continuum, there's a scale symmetry, but there's no conformal symmetry. In fact, we don't even have rotation symmetry.
I see. Okay, thank you.
I'm giving you no guarantee that all systems have scale symmetry.
Okay, thank you.
Hello. Yes. So I just had a question about this. So all these theories that you had presented did not have rotational invariance, and they were non-relativistic kind of theories. But you had also made a comment that you could get a relativistic theory and maybe turn on a background and then get these theories. Is that?
No, I did not say that. I said the fact that the system is not rotationally invariant is not that surprising, because you can always turn on background fields in a rotationally invariant system and find a non-rotationally invariant system. These systems are actually a little bit more subtle because they include fields in representations which are not SO3 representations, only representations of in this case, Z4. So for example, AXY is spin 2, but we don't have AXX and we don't have AYY. We have only AXY. So it isn't a representation of Z4.
But is there like a relativistic theory where you can go to a like a symmetry broken face where you can get this, or is there some kind of a no-go theorem that you cannot do it?
I do not know. I do not know the answer, and it might be that there is a system that has the fullest. So on the lattice, there's never a SO3 symmetry, so you can't even ask this question. I think the question you really ask is there an SO3 invariant continuum Lagrangian where we add more couplings and more interactions and we spontaneously break SO3 to this lattices, to this a cubic symmetry group. And I do not know the answer to that. But on the lattice, there's never the other symmetry. And I also emphasize here that it's not only that the coupling constants violate the SO3 symmetry, but also the fields themselves are not in SO3 representation.
Okay, thanks.
Any more questions? Okay. Well, thank you, Nati, for a delightful talk. It was great.
Thank you for inviting me.
Please I would request everyone to please unmute and thank Nati again by clapping.
Thank you very much.